In the previous lesson, we talked about sequence and series, and of course, we started to talk about arithmetic sequence and series, whereby we said that if you wanted to find the sum of a series terms, let's say you have 1 plus 2 plus 3, all the way up until you arrive to some value n, we said that we usually write this with a sigma notation as an I there, and here we say our I is running from from 1 up until you arrive to n. So this is the same as that, and of course we actually came to a conclusion that this whole thing is always gonna be the same as n times n plus 1 all over a2. And we said that this is an arithmetic series because we are having the pluses. And we also talked about the series of terms of quadratic. We talked about a quadratic series, which is, let's say we are having an I squared here, where I is running from 1 up to n, whereby we are having 1 squared plus 2 squared plus 3 squared plus 4 squared up until you arrive to n squared. And we said that actually this whole thing is simply the same as n times n plus 1, and then we have 2n plus a 1, and then we divided by a 6 there. And then we also moved to actually cubic of this type, whereby you are having I cube, and then you have your I, and your I is running from 1 up to n. Of course, when we're talking about this whole thing, we're talking about you have 1 cube, and then you have plus 2 cube, and then you have plus 3 cube, and then you have plus up until you arrive to n cube. We said that this one is supposed to be the same as that of an arithmetic, except that we are having a square there. So you have an n plus 1 divided by a 2, and then this whole thing you raise a 2 into it. And then we also talked about geometric. Okay, this one was arithmetic. This one arithmetic series, and then this one here was a quadratic, so it was a quadratic series. And then this one we said it is actually a cubic. So we ended up having this and that and that. Of course, we tried to generalize even if you are not having these nice terms like this. And then we also talked about geometric series, which is of this type. You have a times r raised to n minus 1, whereby this r here is a common ratio, like you are having a t2 over t1. This is actually this r, and of course this n is the number of terms in that sequence. A is the first term of the sequence or series. So if it is running from 1 up to n, we said that this is always gonna be a times 1 minus r raised to n all over 1 minus r. Of course, you can see here that the number of terms here is the same as the number of terms that are here. And the next thing, most students usually confuse this. You have a minus 1 here, so we always add a 1. This n here is actually how many terms are in that series. It has nothing to do. Don't try, hey, there's a no. Just look at this n here. This n is actually the number of terms in the sequence that you are actually dealing with, or series that you are actually dealing with. And also we talked about, remember that when we're writing this sum with n there, this is the same as s of n. And then now we talked about this one is a geometric series. And then now we started to talk about the sum to infinity of a geometric series, which is just the same. This is the same thing. I don't want you to get confused as n approaches infinite of whereby here you are actually having I is running from 1 up to n, but you have this limit here, and then of course inside here you will end up having this a r raised to n minus 1. And if you look into this is only going to be possible if this r is less than 1 and is also bigger than minus 1. So this one we said that is always gonna be the same as a divided by 1 minus r, where our r is less than 1 and is also bigger than minus 1. That is actually the sum to infinity of a geometric series. So if you look into these things, they were very nice to actually deal with. And also another thing that I wanted to add here is this. This thing here is also the same as the sum from I equal to 1 running from 1 up to infinity of a raised to r raised to n minus 1. I don't want to say you did not say any of these things. I want you to just be aware that this thing here written like this is the same as that, is the same as that. The same thing here, once you have this sigma notation and you're running from I from 1 to n, you must know that you're talking by s of n. The same thing here, this is s of n, this is s of n, this is s of n. But today I want us to talk about antiderivatives and the area under the curve. So that's what I want us to look at. Of course, this little background here, we will need it. So I want us to talk about antiderivatives. Derivatives. And the area under the curve. The area under the curve. In other words, what is the relationship between antiderivatives and the area under the curve? Let's start with the first example here. So we have our first example so that we can see what we're actually talking about. So let's look at the first one here. The first question is saying, what is the area? So the area of the shaded rectangle on the interval. So we have this interval here, and this interval is moving from 0 to some point x bounded. So there's a region that is bounded by the line y is equal to 5 and the x axis. Okay, so basically here, if you look into this statement, you are actually having, let me place a Cartesian plane here, a Cartesian plane there, and of course you will notice that this is moving from negative infinity to positive infinity. And then of course these are the x-axis, these are y-axis, and if you look carefully here, we have a constant function that is moving from negative infinity to positive infinity. So, and this function of ours is y is equal to 5. In other words, here this point is 5. And then here we are having a 0, and somewhere there we have some point x. So we have a rectangle somewhere there, and this is the region they are talking about. So that is point A. What is the area of the shaded rectangle? And then I want us to look now at, I think I'm going to do this here. And then the question B is asking, if f is the particular antiderivative of the function. So of the function y is equal to 5. What is the value? So what is the value of, I am going to take f of x minus f of 0. So what I want you to see here is that this x here, it is this x that is here, it is this x that is in the interval. This 0 here is this 0 here, which is this 0 here. I want you to see the relationship between the area under this curve on this interval and actually the value of this. You take the antiderivative and then you subtract the outputs at these points here. So that is actually the main goal of what we are doing here. So we are going to have our solution here, right? So if you look here, the area, I'm going to call it with A, of this rectangle here is always going to be the base. I'm always going to have a base times the height, because this is just the rectangle. You take one side and that side. The base is the length that is moving from this point to that point. Of course, moving from here to there, that's actually x units. So we'll actually end up having x times, and then the height is from 0 up to 5, so it's actually the length is actually going to be 5 units. So we're always going to multiply by 5. So we have 5 times x. So that is actually the area under the curve. And then we have this area here I want us to highlight. We have this area, and this area is evaluated between these 2 points. Now, what is actually the particular antiderivative of this? I want you to take note here that I'm going to have my solution here. If you are having a function y, and this function is 5, you must know that it is 5 times x raised to a0. And then the antiderivative, so our f of x, remember that now we're not looking for the most general, so we don't need that constant. We are looking for the particular, so we don't care about that constant at this stage when we are dealing with the area. Now, when you look into this one here, of course, you'll just have a 5 and you'll have an x, and then you have a 0 there. You need to add a 1, and then you divide by the new exponent. And of course, 0 plus 1 is just going to be a 1. So we have 5 times x raised to 1, and then divided by 1. Of course, this is just 5x. So if you look now at f of x minus f of 0, you will notice that I will have 5x, which is this f of x, minus 5 times a0, which is the same as just 5x, because this is going to be a0. So what can you say about this having a 5x and also this one having a 5x? So this is the relationship that we are actually having, that the net area under this curve between these 2 points is actually the same as just the difference of the outputs of this antiderivative. So that is the relationship that we're actually having here. And I'm talking about the net area here, because if, let's say, there was part of this shaded region that was below the x-axis, it was going to be negative and it was going to reduce the area. So it is a net area, not the total area. So that is what I'm talking about here. Let's talk about another example. I like some examples because they give clarity on what we actually are doing here. So the second example, we still have A is saying, what is the area? So we want to find the area of the shaded right angled shaded right angled triangle. We want to find the area on the interval. The interval must be given on the interval. So now we are moving still from 0 to x, bounded. No, this is not bounded. Bounded by the line. Bounded by the line y is equal to x, and the x-axis. X-axis. Now, let's first draw this statement here, what is being said here. So if you look into this, you will actually have this, the y-axis, the x-axis, of course. So now that we are having this nice thing here, I want you to realize that we are having a y here, you are having an x. And of course here, we are having, no, this one is not a good looking line. Let me do that. So we're having something of this type here. This is going like that, this is going like that. And of course, this is the function y is equal to x, which is this one here. And then 0, we know that 0 is here. And then x, our x, I'm going to say our x is somewhere there, so that at least we know that we are having our x there. Just for you to notice, this is a right-angled triangle if you look here. And then the next thing that I want us to realize, the area they are looking for, they want us to find this area that is shaded there. And another thing I want you to realize, that if you actually looking for this point here, this point is on the line here, and the x value here is just x. So this point here, the x coordinate is x, and when I'm plugging it here, the y coordinate is also going to be x, because y is equal to x at all the points that are on the curve. Which means this one here, moving from this point to that point, we are having an x, and moving from this side to that side, we are having an x. So we wanted to find the area of that. And then the second question here, which is going to be B, is saying if f is the particular, so it is a particular antiderivative of the function y is equal to x. Evaluate. So we wanted to evaluate f of, I want to go to these intervals. The interval that was given was 0 and x. So this one here is the one that we always start with, and this one is the one that we always subtract. So this one, I'm going to start with x. So here I will have an x minus f of 0, which was actually given. I want to find out what is this, evaluate this. Let's go back to this triangle here. What is the area of a triangle? An area of a triangle is always going to be 1 over 2 times the base here times the height. So we have an height there, 1 over 2. And then moving from this point to that point, this is just x units. So the length of this line is x. So I'm going to multiply by x. And moving from this point all the way up, you can see that the height is also x. So I'm going to multiply by x. So this is going to be 1 over 2 times x squared. So this is actually the area of the shaded region that is below this line here. Now, let us look at the antiderivative. Look at the solution, of course. So the antiderivative of this function here, x. I want you to realize that we were having an x. Of course, there was nothing there, which means there was a 1. So you are going to end up having a 1. This is a particular antiderivative of that. So this is going to be 1 plus x, and then you divide by the new exponent. So this is going to be x squared divided by 2. Of course, we don't have a constant here because we are talking about the particular antiderivative, not the general, the most general, because the most general have a constant of integration, which is that plus c. Then when you're looking at this, let me write it down. This is a particular antiderivative. And of course, now when you're looking at f of x minus f of 0, you're going to get x squared divided by 2, and then minus 0 squared over 2, which is just the same as x squared over a 2. And if you look at this value here and look at that value there, you can see that they are actually the same. That is actually what we are actually having in this particular case there. Now, I want us to talk about something now that is much more interesting and also much more, don't want to say intriguing, but let me put it as it is interesting. So I want us to find, if let's say, let me just draw this function first, the graph. Make sure that it is big as possible. And I want us to actually talk about this, because once you understand this, then you will actually understand what a definite integral is. Because if you don't understand what I'm going to do, then you actually don't understand what is a definite integral and what is the relationship between the definite integral and the area under the curve. Because truthfully speaking, that's just the net area if we are talking about the definite integral. So suppose I am giving you a curve here. I'm going to try and give you a very smooth curve. So this is the curve that I'm about to give you. So this is the curve. I'm just going to give you the most general curve. It's just going to be like that. And then from this point, let me just clean this up and have that. And then also this side, I'm going to clean it like this. So this point here down there and this point down there, I'm going to call them something. So let's say now this point I'm going to call it A, point A. And then this one I'm going to call it point B. Because I wanted to have an interval A moving from A to B along the x-axis. So my x is somewhere here. Now, I want us to find the area under this curve. So this area is the area, not area, is the area under this curve between the curve and the x-axis. So that is what I want us to find. So how do we end up doing that? This curve here is the curve, let's say y is equal to f of x. So it is some function. I am not saying that this function is only looking like this. It might happen that the function is looking like that. It might happen that the function is looking like that. So it doesn't matter. We can have that or have that or have something like that. I'm just giving you this smooth curve so that you can understand what I am actually talking about. Now, how can we actually find the area under this curve? Take note that it was easy for us to deal with this because it was a triangle. It was easy for us to deal with this because it was a rectangle. So now, how can we find the area that is actually bounded by the line passing through A and the line passing through B, the x-axis and the curve? How can we find that? So the first thing that we actually do here, we divide this this space here into equal. Okay, let me put it like this. From this point here, we divide this interval AB into n equal parts. That is the first thing that we actually do here, because we wanted to approximate this area by using the area of a rectangle. That is why we are doing that, because it's easy to find the area of a rectangle, length times you can say width times breadth. That's what we can actually do to find that. So once you are having a box like this, let's say something like that, a rectangle like this, you just take the length of this side times the length of that side, and then you are done. So this is the easiest shape that we can actually manipulate and actually deal with. So the first thing that we actually do, we just decide to break this interval here into sub-intervals, equal sub-interval. Of course, I'm drawing this with by hand, so it's not going to be equal, but I hope you will be able to actually get what I'm trying to do here. So the first thing, you divide this into equal intervals. So that's the first thing that you actually do. Divide this into n equal sub-intervals. So this length, let's say, if you look into this length, I don't need that. This length and that length, all this length, that length, they are equal. And these lengths are actually called delta x. And this delta x is the same as b minus a divided by n, because this is the number of intervals or sub-intervals that I need here. So that's the first thing that you do. The second thing that you do, this one you're gonna call it x1, this one is going to be x2, this one is going to be x3, all the way until here you are having xn minus 1, so that a is the same as x of 0 and b is the same as x of n. So that is what is happening here. x0, x1, x2, x3 up to x of n minus 1, and b is x of n. So that is what is actually happening here. And if you look into this position here, this is actually delta x. I mean, the length moving from this point to that point is delta x, which means that at this particular position, you can actually determine what is the value of x1. So you are having that. I hope I'm explaining that. The next thing that you wanted to do, you want to draw a line, a vertical line that is actually going to the curve, and then a vertical line that is actually going to the curve, a vertical line that is actually going to the curve, a vertical line that is actually going to the curve, a vertical line that is actually going to the curve, a vertical line that is actually going to the curve, and a vertical line that is actually going to the curve, and a vertical line that is actually going to the curve. Of course, you proceed by doing all these things, because we wanted to approximate this and get the general formula for finding the area under the curve for all the function. If I give you a function, you just use that formula, and then after that you will be able to get the area under the curve. Let me first copy this because I will need it again. I'll copy it twice. So let me copy, and then I'm gonna paste it here. Okay, I think it's fine even if it's here. I'm gonna copy it here again. We'll deal with it piece by piece so that we can go and take some nice examples if possible. Okay, now that we are having that, the next thing that we actually end up doing here is this. We first make sure that, remember that these are x1, x2, x3, and then some dots. Of course, somewhere here you will end up having some xi minus 1, and here you will end up having some xi, and then we continue up until we arrive to that point there. Now, once we actually end up doing this thing here, this is what I want us to actually realize. If you look at this point here, this shape here, I'm gonna call it, let's say this one, this part, only this part is S1. I'm gonna call this S2, and then I'm gonna maybe this one S3, and then go all the way. This is going to be our SI, and then of course up until we have S of n, right? So if I wanted to find the area under this curve, I just need to find the area of this, area of that, area of that, area of that, area of that, and then I sum them up. So that is actually going to be the area that is under this curve. So I just need to just add these areas of each of these things. Excuse me. Now, If you look into this thing here, I cannot find the area of this because I don't know how to deal with this shape here. But what I'm going to do here, I'm going to approximate this area by a rectangle. So what I'm going to do, the first thing of the rectangle that I'm going to try is to use this this position here, or the right end point of this interval here. So this interval as the height. So if I'm using that as a height, so the height of my rectangle will end there, and then of course the rectangle that I will have is gonna be there, and then even for the same for this one, the same for this one, the same for that one, the same for that one, and I continue to do that, and I continue to do that, and I continue to do that, and you can see that this is actually going smooth, and now I have these rectangles. So if you look into this here, now the area under the curve is actually going to be, in order for us to actually approximate this area, you will find out that we can actually approximate this area by, if you look into this, the height at this point here. If you look at this point here, what is the value of the function? The value of the function is actually going to be the height of this rectangle. So it's going to be f of x1. And then if you look here, it's going to be f of x2. And then look here, it's going to be f of x3, and so forth up until you arrive there, f of x of n minus 1. So these are the height. And the base, because these are equal, each base is, this base here is actually equal to this one here. So basically, to approximate this, we just end up having to say, I'm going to take the height, which is f of x1. I'm going to have f of x1 times the base plus f of x2 times the base, and then plus up until I arrive to f of xn, because f of xn is actually going to be the last, because I keep taking these ones here. Take these ones, take this one, take this one, take this one, take this one, take this one. So we have x of n, and then times delta x. And of course, you know that this one is the same as just f of b, because xn is the same as b. I want you to realize that f xn is the same as b. So this position here, f of xn is just the same as f of b. That's what I'm actually trying to say. The next thing that I want you to realize is that if you look into this one, it was the area of the first rectangle, this one, it was the area of the second rectangle, and this one, it was the area of the last rectangle, which is here. So we just added the area of these rectangles. The reason I'm saying this is an approximation is because you can see that this part is actually not included. We actually did not consider this part here in this thing that we are actually doing here. So this one is actually not included at all. So we have some error there. So it's not the exact area, it is actually the approximation of this. And now, if you take note in this thing here, I also want you to realize something. I'm going to clean this thing up, and then I'm going to take that one. This area that I'm talking about here is actually, I have this Rn here. I want to talk about this. I'm actually approximating this like this. This is going to be Rn. I have this approximation. So this Rn here is actually the same as that. I'm going to explain why I'm saying it is actually the Rn. If you look at this one here, these areas, I am picking the height. If you look at this interval between a and x1, I am picking this point here, which is actually on the right of this interval, on the right. And also when it comes to this one, I am picking this height here, which is actually on the right of this interval, on the right of this interval. So this R here is actually saying we picked the right end point of each interval. So this r, that's just the meaning of that, this r. That's why we usually have this r when we're dealing with that. Now, the next thing that we do here, if we want the exact area here, imagine if, let's say, I increase this n. In other words, when you're increasing this n, you want to have as many intervals as possible. I'm going to use this thing here to explain what I'm saying here. So if I increase this this n, we will have another interval here, another interval there, another interval there, another interval there, another interval, another interval, another interval, another interval, and so forth. And you will find out that when I'm picking my height, let's say here, my height is going to be there, right? And then if I pick another interval again, I will have another height, of course, another height there, and 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 another height, of course. I pick another height, and so forth. So if I decide to add another height, of course, there, to have as many intervals, in other words, I'm increasing n, you will see why I'm doing these things here. I add another height, I add another height there, I add another height there, I add another height there, I add another height here, I add another height. You will notice now that when I'm actually creating the new rectangle, so it's going to be this rectangle. You can see now that the area that is going to be, that we're missing, is going to be there, and of course it's going to be smaller, and of course the area is going to be smaller, and of course the area, the error that we're actually having, is going to be smaller and smaller. And you can even see that once we are here, we have this, and of course we have that, and we have that, and we have, and what I want you to see is that now the error is so small. Let me remove that. The error is so small, it's only these pieces here. It's only these pieces here. And now the error is smaller than the previous error. But if I increase and also add another height there to have as many rectangles as possible, this error here is going to be very small, and it's actually will end up getting the exact area if we keep adding as many heights as possible. So with that being said, the exact area, let me write this, the exact area will be found by making as many rectangles as possible. That is what I'm actually saying. Or simply put, increasing this n as possible to make sure that the length of each rectangle is actually so small. In other words, now the exact area is actually going to be achieved by taking the limit as n approaches infinity. So we're increasing n unboundedly. And then we have this Rn, or simply put, it is the limit as n approaches infinity of f of x1 times x delta x plus f of x2 plus times delta x plus blah 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 up until you arrive f of x of n times delta x. So this is just telling us that make as many rectangles as possible, so that these rectangles have smallest area as possible. That is where this limit is coming in. And of course, this is actually the same as just the limit as n approaches infinity of the sum f, where I is moving from 1 up to n, and you're having f of xi and times delta x. So this thing is actually the same as that. It's just the notation, and this r is telling us that we actually picked the area, we picked the height on the right end point. So that is what this thing is actually telling us. I hope you can see what is actually happening here. That this delta x is actually, you take this endpoint and that endpoint and then you divide by n and make your n as large as possible so that you get areas of smallest rectangles. Of areas, rectangles of smallest area possible so that you can add them and get the nice thing. The next one now is instead of picking this one here, you decide to pick the one on the left. So if you are picking the one on the left, of course, your rectangles will be like this. Your rectangles will be like this. Your rectangles will be like that. And then you end up having these rectangles. And then you will end up having this rectangle. That's actually the second method to do this. If you don't like picking this one, you want to pick the left end points. So you will end up having your rectangles like this. And this is actually the second way. The first one is always going to be this are the right one. And for that, if you are doing that, your area now is going to be the limit as n approaches infinity of r of n, which is just the same as the limit as n approaches infinity of the sum where I is running from 1 up to n, and here we're actually having f of x. I'm gonna put I minus 1 times delta x. What is basically happening here is that the approximation, actually, I'm going to talk about this one in a moment. The approximation here is saying to us that we have the area is approximated by, let me just put this for now, and then we'll talk about it. And I will have, at this point here, because I have to pick one on the left, I will have f of x of 0, which is just the same as just f of a, and then times delta x plus, when we are here, I will have f of x1 times delta x, and then we'll continue all the way until we arrive here, and we'll have f of x of n minus 1 times delta x. And if you look into this thing here, it is the same as that. That is why we have a minus 1. This minus 1 is just saying that take the one on the left, and of course here we're supposed to end up having x0, and x0 we know that it's the same as just a. Now this r here, we said that we are picking the right endpoint. For the left endpoint we pick L, for the left endpoint we pick an L, to say that we are actually talking about the left end point. So we can do that. The next thing that I want you to realize is that whether you pick this one on the left or on the right, the fact that you are actually making your n so large, this area is going to be the same as that area even if you picked on the right hand side. So that is actually what is important here. The last one, we can decide that whenever I have to pick the point here, I pick a point somewhere there, so that when I'm actually giving its height, the error is mixed mild. Let's say I pick it here. You can see that once I pick this point here, I'm gonna tell you what this thing is. It's not exactly in the middle. So whenever I have this rectangle and that rectangle and that rectangle, this is how I pick it. I pick this point so that this, at this point here, at this point, remember that, what's this? Let me remove that. At this point here, we'll have f of something here once we know the value there. So this is the third method. This is the third method. So when you look into this one here, this point is chosen such that the error is minimized, so we don't add more area and also we don't subtract more area, because if you look here, there is this error here. There is always going to be that error that is added, and also if you look here, there is always that error that will be missed, which was the red one. But the more we minimize that error, we minimized it by increasing this n. And also here, this error was minimized by increasing this n so that we end up getting something nicer. Now, when you look into this one here, you will find out that this thing here, once we pick a point so that the height will be on the curve. But when you are picking this point here, you will end up having the height is going to be of this type. So we'll end up having a height. And if you look at this area, we actually excluded this area. But when you're looking at this this part here, we actually added it back. So we actually choose this point here. We usually say this point and we place a star there, and we have a 1 because we're dealing with the first rectangle. We usually put it like that. So you can see that this point is chosen in such a way that the area that we lost is actually gained somewhere. So we minimize it like that. This point here, whereby you choose it in such a way that we minimized the error, is called a sample point. So it is a sample point. So a sample point is a point in the sub-interval such that the area of each rectangle is minimized. That is actually the sample point. So when we wanted to find the area using the sample point, we will actually end up having the limit as n approaches infinity of the sum as I moves from 1 up to n of f of x. We have this dot there to say it's a sample point, and we have at some rectangle there times delta x. Now this is what I was saying. The height, of course, this point we said that it's a sample point, so here we'll end up having x1 star, and then here, of course, we'll end up having a sample point, and the height is going to be like that. And this point here, which is going to be the height, is going to be f of x2 star. So these are the sample points. So I hope I have covered some of these nice basics here. But because this is same as the area, it is the same as this, it is the same as that, the calculations will give us the same thing. So what is important here is this. I want you to realize that the area can be found by the limit as n approaches infinity of the sum of f of xi times delta x, where I is moving from 1 up to n, or you can find it by having your limit as n approaches infinity, sum from I raised to n of a, of that, and then you have your f of xi minus 1 times delta x. Taking note that we take note here that x0 is the same as a, and here we take note that x of n is the same as b, because we'll end up arriving there, and if you're separating a 1, we'll end up getting that one. And also the next thing here, you can also find it by saying your n approaches infinity of the sum as n is equal to 1 to n of f of x star I times delta x. So you can either use that or use that or use that. You will get the exact same area. One thing that I want you to realize, I'm going to give you examples on how to use this one, because when it comes to using this one, it's the same as that. When it comes to this one here, mathematics become tedious, but you will get the same answer because you will end up having to pick this for each and every angle. And most people usually end up choosing the middle point. It's not always the point in the middle of each interval, this point here, because most people say, no, this point is in the... Not always. It's not always. Sometimes you find out that whenever you are picking in this interval, this sample point, maybe in one of the rectangles, it needs to be close to that point, and that's just a tedious mathematics. So we're not even going to look into that, because all I'm telling you that this one and that are equal, so we will deal with that. And also we're not going to look at the examples for this. Let's just look at the examples of this one and how to use it and see. Of course, we want to compare with the what I usually call it the the antiderivative, the difference between antiderivatives. Before we move forward, there's also something that I want to mention here, but we'll do it at a very last stage. If you notice here, this area that we're talking about above, we usually denote it like this with this symbol, whereby if you look here, this point here, which is the smallest point, we write it here. And this point that is here, we write it there. The given function, we write it here. And then we write this thing theta x. So when someone is writing something of this type here, you must know that they are actually talking about this area that I've been explaining. I don't want you to get confused, because this nice thing that is happening here, it is just the same as this area that I've been talking about here. In other words, this is just the same as the limit as n approaches infinity of the sum as I raised from 1 up to n of f of x star I times delta x, or simply put, it is the limit as n approaches infinity of the sum from I is equal to 1 up to n of f of xi times delta x, or simply it is that, depending on which height do you want it to use as the height of each of the rectangles. So we pick this, which is the same as also f of x I minus 1 times delta x. I am starting with this one because the textbooks, when they are trying to define this, they define it according to this one, but this and that is one and the same thing. And for the examples, I'm just gonna use that. I hope I have specified that the area and this symbol like this, if they are asking you about this symbol, something like this, you must know they are actually looking for that net area. So it's one and the same thing. I am still going to redefine this at a later stage, but I just want you to know now, because I've talked about this area. What is that area? Let us look at the examples and see what we can actually do. I hope I do have some examples here. So let's start with an example. I'm just going to take 2 examples. And of course, after that, I define this thing and then tell you what this symbol, what each of the symbol mean. And then after that, in the next lesson, I will actually go through some of the terminology that is actually used. It's not hard, it's just they are trying to confuse you with all these terms and all these symbols. This is just the net area that I've just explained above. So we are having our A here. Our A is saying, what is the area? So what is the area enclosed? What is the area enclosed by the line? What is the area enclosed by the line y is equal to x squared? Sometimes they say the line or the function. The x-axis. The x-axis and x-axis and the line x is equal to a 2. What is the area? They want you to find that area. The second question is going to be, let me write this second question right here, because the answers of this will be a little bit longer. If f is the particular, so we have f is the particular antiderivative, are there particular antiderivative, right, of the function y is equal to x squared. Evaluate f of, I remember that here we have this function and also we have this as the end point, so we have a 2 there minus, and this function passes through 0. I wanted to evaluate from f of 2 minus f of 0. Evaluate that. So that is what we want us to do here. So let us deal with the solution here. I'm going to write my solution somewhere there. So we wanted to find the area. So the first thing that you have to make sure of, I want you to actually first understand the meaning of doing this so that you don't end up getting stuck. What is the area under the curve? What is this? So we are actually having our a first. I'm gonna deal with a first. So the function, it looks like this. So this one is y is equal to x squared, and this side it looks like that. So here we have what is the area enclosed by the line y, the x-axis. So we have the x-axis and the line x is equal to 2. And in this example here, there's also something missing here. We should have added y-axis. Y-axis need to be there. So if you look at this y-axis are here, x-axis are there. So we wanted to look at the area that is actually not passing through this. So these are the y-axis. Now x-axis are here, and then this line here, and then there is a 2. So x is equal to 2 is somewhere there. So y-axis and this one and this, so it must be this area here. So our x, here we have x is equal to 2, here we have a 0. Now, I want you to realize something here that I also wanted to have. Remember, we have this 2, that 2 is that, and this 0 here is the initial point, it is that in B. Now, the next thing that I want you to realize here is that you need to find delta x. Delta x, you take this point and then you subtract that. So we have 2 minus 0 divided by an n, like we did in our explanation there. So our delta x is going to be 2 divided by n. That is the first thing. The second thing that I want you to realize is this. If, let's say, I were to look at f of xi, because I'm going to use Rn, that's what I said, all these examples I'm going to use this. So if I take a point xi along the x-axis and I plug it in this given function, what will I get? I will get xi squared. That is also something that I want us to actually realize. And if you go back to this function here, I want you to realize that if I were to draw one rectangle here, the first point is going to be there, the second point is going to be there, and my rectangle is going to look like this. And this one here is going to be 0, and this is going to be x1. And to move from 0 up to x1, I need to make sure that this interval here is the same as 2 over n. So to move from here to there, this is going to be 2 over n. And to move from here to x2, this point here is also going to be 2 over n. And to move up to x3, if we have x3 there, and then this point here is also going to be 2 over n. So what is basically happening here? To move from this point to that point, I need to add from 0 this thing here, so that my x1 is going to be 2 over n. And then to find my x2, I'm just trying to analyze here. I have to add, let me rewrite these things here. Here I have 0. I have a 0 somewhere there. This is 0. Now the intervals are equal. In other words, to move from 0 up to x1, this part here is delta x. And I know my delta x is 2 over n. And also this is x1. And then here we have x2. And I know to move from here to there, it must be the same as moving from here to there. So this is also delta x. So to move from here to there, to x1, I must know that the point here, I'm going to have 0 plus this, I will get that. So we'll have this one is going to be delta x, which is the same as 2 over n. To actually arrive at x2, I need to say this length here, delta x plus this delta x. So we'll end up having 2 delta x, which is just the same as 2 times 2 over n, which is the same as 4 over n. That is what is basically happening here. And then when you're going to x3, this is just going to be the same as delta x plus delta x plus delta x, which is just the same as 2 over n plus 2 over n plus 2 over n, which is just the same as 3 times 2 over n. I hope you can see what I'm trying to do here, so that you can see that x1 is just the same as 2 over n, and x2 is just the same as 4 over n, or 2 times 2 over n, and then x3 is just the same as 3 times 2 over n. That is what I want you to realize here. As long as you can see that this delta x is the same as 2 over n, and then f of xi is the same as xi times raised to a 2. So we are good. And also these things here, you can arrive at them. You know that the first one, if we're moving from 0, is going to be the same as just delta x, 2 over n. And then the second one is going to be 4 over n. And the third one is going to be 2 over n. That is what I want you to realize. Now, the second thing now, we know that our area, of course, we said our area is going to be written. In most cases, we usually write it like this. This is the initial point, and that is the end point. So we are going to have a 2 there, and we also here we are going to have a 0 here of f of x, and then we have this dx there. How do we end up evaluating this? Of course, we are looking for the net area there. This is the limit as n approaches infinity of, we know that what is actually supposed to happen inside here, we're supposed to have f of x1 times delta x plus f of x2 times delta x plus blah 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 up until you have f of xn times delta x. That is what we're actually doing here. And then of course we can actually move faster. You have the limit as n approaches infinity. And then inside here, what is f of 1? That is actually the most interesting thing. I know that my f of x is just equal to x squared, because that is actually the function that is given. F of x or y is just x squared. That's what I wanted to know. And then when it comes to this one here, I know that I will just have x1 squared times delta x. What is delta x? Delta x, we said it is 2 over n. You see how easy this thing is. x2 squared times 2 over n plus blah 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 up until you arrive xn squared times 2 over n. This is not hard at all. You can take this thing out, and then you will have the limit as n approaches infinity. And then inside I will have not inside, outside I will have 2 over n, and then inside I will have x1 squared, and then plus, and then here I will have x2 squared plus x3 squared plus blah 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 up until you arrive to xn squared. You can see how easy this thing is. The next thing that I want you to realize here is that we have n approaches infinity, and then here I still have a 2 over n, and then inside here I still have my x1 here. My x1, I said it is the same as just delta x. It is just a delta x, or 2 over n, and then I want to square that thing, plus when it comes to this one here, x2, it was 2 times this over that. So here we'll end up having, let me write something here so that you can see. It is 1 squared times 2 over n. 1, you know that this, even if it's not there, it's still not going to change anything. So let me just write that. I will go back to it at a later stage. This one, it is 2 times 2 over n, and then you are squaring it up. According to what we found there, it was that 2 times 2 over n. And then when it comes to this one, of course, it's going to be 3 times 2 over n, and then you square it up, plus blah, 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 up until you arrive to n times 2 over n, and then you square it up. You will see this thing is not even hard. And then you have the limit as n approaches infinity, and then you have a 2 over n. And then inside here, you will find out that when I'm having this thing here, is 2 over n, which is the same as just 1 times 2 over n. So we have 1 times 2 over n. 1 times 2 over n is just the same as 1, and then we square it up, 1 squared times 2 squared over n squared. That is also something that is so much important. The next thing here, we'll end up having 2 squared times 2 squared over n squared plus 3 squared times 2 squared over n squared plus blah 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 plus n squared times 2 squared over n squared. So that is also something that we're actually getting out of this. What did I do here? Okay, I think we're still good to go. The next thing that I want us to realize here is that I have 2 squared over n squared, 2 squared over n squared, 2 squared over n squared, 2 squared over n squared. I'm going to pull it out. So I'm still having the limit as n approaches infinity of 2 over n times what I'm going to get there, 2 squared over n squared. I am actually pulling it out. And then inside I'll be left with 1 squared plus 2 squared plus 3 squared plus blah 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 up until I arrive to n squared. And then if you look carefully into this, you will actually find out that this is just the limit as n approaches infinity. And then here 2 times 2, when multiplying powers of the same base, you add exponents. So this is going to be 2. Of course, 1 plus 2 is just a 3 divided by n raised to a 3, because there is a 1 there. 1 plus 2 is a 3. And then inside here, I want you to realize that actually this is something of this type here. I have 1, I have 4, I have 9, I have, if you look here, this 1 squared is 1, 2 squared is 4, 3 squared is 9, and then the next one is going to be 4 squared, so it's going to be 16, the next one is going to be 25, and these things, they continue forever. If you subtract 16 from 25, you will actually get a 9. So you can see here 25 minus 16, you will get a 9. And then 16 minus a 9, so I have a 16 minus a 9, that's actually a 7. And then from 9 and 4, you will find out that actually this is a 5, and 4 minus 1 is a 3, and 9 minus 7, that's a 2, 7 minus 5 is a 2, 5 minus a 3 is actually a 2 also. So this one here that we're actually having is a quadratic series. And since this one we have 1, 2, 3, 4, 5, we know its formula, as we said, and we know the number of terms here. The number of terms is n, and of course this is actually going to end up being something we actually said it was actually going to be an n, and then you will end up having an n plus 1, and then you will end up also having your 2n plus a 1. You divide this whole thing by a 6. That was actually the formula we had in the previous lesson. And also, of course, we actually summarized and talked about it. So you can see actually this is actually not that hard at all, because it is just a quadratic series. So we have a quadratic series that is so easy here and easy to deal with. It's not that hard at all. I don't want you to end up being too scared. You see this, you know how to deal with limits, and you know how to deal with sequence and series, especially the basics one that we're doing. We're not gonna do so much things like a factorial and other things, macroequations. We don't do that in this course. It's not part of your syllabus. Just focus on the basic ones. And then of course, if you look into this, this is just the limit as n approaches infinity of 2 to the power 3. You know that's just the 8. 2 times 2 is 4, 4 times 2 is 8. And then we divide. I have this 6 here, I'm going to place it here. And then inside here, I will have n, and then I will have n plus 1, and then I will have 2n plus a 1, and then divide this whole thing by n cube. And then from there you can see that n cube, I can just cancel this 1n and one of these n and end up having a 2 there. Let me not, it was a 3, cancel it, you have 2 of them. And then the next thing is going to be, I have, because these are constants, I can pull them before the limit. There's no harm in doing that, so that I can focus on things that actually make sense. So we have this n plus 1, and then multiply by 2n plus 1, and then divide this whole thing by n squared. And of course, this is going to be 8 over 6 times the limit as n approaches infinity. And then inside here, I'm going to expand this. N times 2n is going to be 2n squared. And then n times 1 is going to be n. And then 1 times 2n is going to be 2n. And then 1 times 1 is going to be a 1. And then divide by n squared. And then if you proceed here, you will find out that we have 8 over 6. And then you have a limit as n approaches infinity of, I'm going to simplify this, I have 2n squared, and then plus n plus 2n is going to be 3n plus a 1 all over n squared. So once you are having this thing here, the next thing that I want you to realize, you can see that this limit is going up to positive infinity. So you can use L'Hopital's rule. There's no harm in doing that. You can use other methods of dividing this whole thing by the highest power of the denominator. I don't care how you do it from here, but I hope you can see which method that I'm going to choose here. I have a 6. And then here I have a limit as n approaches infinity. You can use L'Hopital's rule, and if you are using L'Hopital's rule, you will end up having to use it twice. So I'm not going to use that. You can use it. The answer is going to be the same. I'm just going to simplify this. Remember that this is just the same as 8 over 6 times the limit as n approaches infinity of 2n squared divided by n squared plus 3n divided by n squared plus 1 over n squared. So this and that is one and the same thing. And of course, this n squared and this n squared will cancel out. And then you have a plus here. And then here you will end up having 3 divided by n, and then here you will end up getting 1 over n squared, still fine. And then of course this is going to be 8 over 6, and then inside here, as n approaches infinity, there is no n here. The limit of a constant, it is always gonna be that constant. Plus, if I plug in infinity here, I will end up having 3 divided by infinity, and then plus I will end up getting 1 over infinite squared. And if you look into this, 3 divided by infinity, 3 is so insignificant compared to infinity, so this whole part is actually end up going to be a 0, because infinity is so big compared to that, so it's going to be 0. And infinite squared is the same as infinity times infinity. And infinite times infinity is a big number times a very big number. You will always get a very big number. And 1 divided by a big number, of course, is actually going to end up being a 0. So here you are getting a 0 and a 0 there. So the next thing you'll end up getting 8 times 2 divided by 6, which is just the same as 16 divided by 6. And then you can start asking yourself, how many 2's are in 16? There are 8. How many 2's are in 6? There are 3. This is actually your final answer. In other words, you can just say area, which is the same as moving from 0 up to 2 of f of x, which was x squared times dx. It is just the same as 8 over a 2. This is the net area. Now that we have this net area, I want us to answer the second question. The second question is saying, if f is the particular antiderivative of the function y is equal to this, evaluate this. So what I want us to do, we are at b now. We wanted to find this f of 2 minus f of 0, of course. Now, Let's first talk about, we have y is equal to x squared. What is the particular antiderivative of this? So we said that f of x is the particular antiderivative of that by the statement. So this one, the particular antiderivative of that is going to be x. We still have an x, we have a 2, you add a 1, and then you divide by the new exponent. Take note that this is not the most general. If it was the most general, we're going to have a plus c, which is a constant. We are talking about a particular, so there is no plus c. So this is going to be x cubed divided by 3. Therefore, you can say that f of x is equal to that, or simply put, what we're looking for f of 2 minus f of 0. So I'm going to plug in 2 there, so I'll get 2 cubed divided by 3 minus 0 cubed divided by 3, which is the same as 2 cubed, that's just an 8 over 3. This one is a 0, so we're getting this nice thing here. Can you note that this second derivative is the same as that? So we are having this area, the area or the net area between these 2 points is that, and actually the net area, the difference between this antiderivative, if you have this particular antiderivative, you take the difference, you get the same thing. I hope you can see that these are the same. Let us also take another example here. Probably this is going to be our last example, and then I will start to define what is important here, which is the definite integral, and then we call it a day. Let us talk about this example. I have a nice example here. Okay, just a quick recap here, just for you to know. The area, this area that we are talking about here, this area here is always going to be the same as the difference of the antiderivative from this point and that point. It's always going to be the case. I just have to save you time, because you will have to go through this process using the definition. But if you are just using antiderivative, it's going to be short like this. That is what is happening. But the definition is actually using what I was using, sequence and series. But if it's not specified that use definition or anything, just always follow this, because you can see that it is not tedious at all. You just have to know antiderivatives by heart. Let's look at another example here. We have A. A is saying, what is the area? What is the area? What is the area enclosed? What is the area enclosed by the curve? Area enclosed by the curve y is equal to e raised to minus x. The x-axis, the x-axis, the y-axis, and the line. And the line, this line is x is equal to a2. So it is x is equal to a2. And then, of course, we have our b. If f is the particular, so f is a particular antiderivative. So it is a particular antiderivative of the function. So it is an antiderivative of the function. You have y is equal to e raised to minus x. What is the value, or evaluate the value of f of 2 minus f of 0. I want you to realize this. Y-axis means y-axis, x is equal to 0 along the y-axis, and then x is equal to 2 is actually plugged in here. We want to compare this and that. Of course, at this stage I just told you that this is always going to generate the same answer, but let's do it because it's just our last example, of course. So let's start with our solution here. So we have a solution, and this solution is actually going to be very easy because in A you just need to find your delta x, and of course because we're moving from 0, our delta x to 2, we have 2 minus 0 divided by n. Where is this 2 coming from? It is this 2. Where is the 0 coming from? Y-axis. So that is what is happening here, which is just the same as 2 over n. If x is equal to 2, let's say here we had a 3, we were going to plug in a 3 here, 3 minus 0. If this x was a 5, we were going to 5 minus 0. If this x was a 10, we're going to say 10 minus 0. That is what is important here. The next thing we wanted to find f of xi. Of course, this is going to be, we have a function, the function that is given is f of x is equal to e raised to minus x. So where there is x, I am going to add this thing here. So I am going to have e raised to minus xi. That is what is important here. The next thing, I wanted to end up talking about x1, and then I also want to talk about x2, and then talk about x3, x2, and then I have an x3, and then I have x4, so that you can see the trend here. So if you look at this thing here, we are talking about the intervals that we are looking at here. Because y-axis we are starting at 0, we are going to have a function that looks like this here. If you look at this function, we have a minus, so it is actually decreasing like that. And of course 0 is here, or the y-axis are here, and then x is equal to 2 is somewhere here. So we are actually looking for this particular area here. And then if I divide my intervals, and let's say my x1 is there, of course now my rectangle will look like that. And moving from here to there, we're supposed to end up having our delta x. And from here to the next one, we also will end up having a delta x. So x1 to move from here to there, at this point here, because this is going to be delta x, so 0 plus delta x will give me x1. So we'll end up, this is the same as just delta x. And delta x, we know it is 2 over n. And then x2, we know that we are moving from x1, is going to be x1 plus delta x. So we'll end up having x1 plus delta x, which is the same as delta x plus delta x, which is the same as 2 times delta x, which is the same as 2 times, what is delta x? Delta x is 2 over n. The same thing here, we'll end up having x1 plus, we'll end up having x2 plus delta x, which is the same as 2 delta x plus delta x, because x2 we know that it is 2 delta x, and then this is going to be 3 times delta x, which is the same as 3 times 2 over n. That is what we are getting here. And then when it comes to this, you can proceed. You can see that this one is just the same as 1 times 2 over n. This one is 2 times that. This one is 3 times that. So this one is just going to be 4 times 2 over n, and then xn, of course, is going to be n times 2 over n. And if you look here, this 4 is that 4, this 3 is that 3, this 2 is that 2, this 1 is that 1. This is actually one of the generalization. And now the area we are looking for is moving from 0 up to 2. Given the function, our function is actually e raised to minus x, and then you have this little thing delta x. So that this is just saying that we have this area there. And then the next thing that you want to know is that by definition, this is the limit as n approaches infinity of inside here, I'm supposed to end up having this, which is f of, I'm going to have an xi delta x, and then I'm going to have I from 1 up to n. And then, of course, this is simply put like this, the limit as n approaches infinity. And then inside here, we just have f of x1 times delta x plus f of x2 times delta x plus f of x3 times delta x plus blah 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 up until you have f of xn times delta x. And then the next thing that you need to realize here, you have to substitute the values. So here, what is f of x1? So looking into this here, if I have f of x1, I'm going to plug in a 1 here, which means I have to plug in a 1 there. So I have e raised to minus f of x1 times delta x. What is delta x? It is 2 over n, plus this one is going to be e raised to minus x2 times delta x, which is 2 over n, plus the third one, of course, is going to be e raised to minus x3 times 2 over n, plus blah 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 up until you arrive to e raised to minus x of n times 2 over n, which is delta x. You can see that this is actually simple. It's just a small strategy. We have n raised to infinity, and then of course I have 2 over n, 2 over n, 2 over n. I want to pull it out so that my calculations are smoother. And then inside I will have e raised to minus x1. And then secondly, of course, you can actually see that I'm having that, and then plus, and then I have e raised to minus x2, and then I have plus, I have e raised to minus x3, and then I have plus blah 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 plus e raised to minus xn. That is what is basically happening now. The next thing, I still have the limit as n approaches infinity of 2 over n, and then inside here I have e raised to minus, what was x1? So if you go back to x1, x1 was the same as 2 over n. That was x1. x2 was 2 times 2 over n, 3 times. So I'm just going to substitute now. When it comes to this, I said it was 2 over n, and then plus e raised to 2 times, we have a minus. Let me put, we have a minus, and then I'm going to have a 2 over n. And then I have a e raised to minus, I have a 3 times 2 over n, and then plus blah 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 up to e raised to minus n times 2 over n. The next thing that I want us to do here, I want us to rewrite this in a nice way so that we can actually see what is the series that we're actually having here. You have 2 over n, and then inside here I have e raised to minus 2 over n. Of course, it is raised to 1 because, it's just raised to 1. And then here, I have e raised to minus 2 over n. Why am I starting with this 2 over n? It's because there is 2 over n here, which is minus. And then, using the power of a power, when you're using laws of exponents, I can plug in a 2 here so that when I'm multiplying this, I get that. And then here, I will have e raised to minus 2 over n, or raised to 3, plus blah 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 up until you have e raised to minus 2 over n, all raised to n. You can see that this is not hard at all. Now, once you look into this, you will find out that if I were to take this term, e raised to minus 2 over n, all raised to 2, and then I divide this by this first term here. So I'm having a t2 divided by t1. What am I going to get? I have e raised to minus 2 over n. This part here is the same as that, so we're dividing powers of the same base. So I'm having e raised to minus 2 over n, all raised to 2. Of course, here we have a 1, so I'm going to subtract. We subtract exponents when we're dividing powers of the same base. And 2 minus 1 is just going to be 1, so we have e minus 2 over n. The second thing, if I'm taking t3 and I'm dividing by t2, you will find out that I have e raised to minus 2 over n, and I divide, I raise this to a 3, and then I divide this by e raised to minus 2 over n raised to a 2. This is just the same as e raised to minus 2 over n. And then I will take this 3 because when dividing powers of the same base, this is the base, this is the base, you subtract exponents. So I'm going to subtract a 2 there. Then I will end up having something nice, which is e, because this is going to be a 1 raised to minus 2 over n. And this one is the same as that. In other words, this series is actually having a common ratio. So this one here is actually what we usually call it a geometric series. So we have a geometric series. So that's what we're actually having here. We have a geometric series. So now that we are having a geometric series, we know the formula for the geometric series. How do we deal with that? Looking into this here, we know that the sum of the first n terms, Sn, is just the same as a times 1 minus r raised to n all over 1 minus r, whereby this r is a common ratio. We already found our common ratio, which is t2 minus t over t1, which is just the same as that. So this is this r. N is the number of terms that we are having. How many terms are we having here? Is n of them. A is the first term. The first term is that whole thing. So how do we proceed? To proceed from here, we can say that this whole thing here is actually going to be equal to the limit as n approaches infinity of 2 over n, and then inside here, this whole thing, I'm going to plug in an a. My a is e raised to minus 2 over n, and then inside I will have 1 minus e raised to, remember that this is still r, so you will have minus 2 over n. And this whole thing, we wanted to raise it to this n, which is the number of terms, and then divide by 1 minus e raised to minus 2 over n, which is our r. Right. Of course, this might confuse you. Why r is the same as the first term? Sometimes it happens. It's not a big deal, because we saw that even here. That actually we ended up having, this is our r and also this is the first term. So that is what is happening. There's nothing that we can do. These things are just the same. So no big deal there. The next thing is just algebra. It's not a big deal also. So we have the limit as n approaches infinity of 2 over n, and then inside here, because here we're having a negative exponent, which means it needs to go to the denominator. In the numerator I still have that, so I'll have 1 minus this n and that n will cancel out, so you have e raised to minus a2. This n and that n, they cancel out, and then divide by e raised to a 2 over n. Where is that? It is this thing, times 1 minus e raised to minus 2 over n. And then we proceed and say we have a limit as n approaches infinity of, you have a 2 over n. You have a 2 over n, of course, 2 over n. And then inside here, I still have 1 minus e raised to minus 2. And then divide this, multiply by that is going to be e raised to a 2 over n. And then this one here is going to be, because if I'm multiplying this with that, I'm going to add exponents. So if I'm adding this and that, I will end up having an e raised to, when multiplying powers of the same base, you add exponents. So I will end up having minus 2 over n plus 2 over n. So that is what we are getting there. The next thing is you want to find the limit as n approaches infinity of 2 over n. Inside there, you still have 1 minus e raised to minus 2 all over. And then I still have e raised to 2 over n minus this and that is going to be e raised to 0, of course, and e raised to 0 is just a 1. That is what we are getting there. The next thing that we want us to do, this one you can see that it doesn't have n at all, and we're dealing with n here. So this whole thing, I want to take it on the other side. So you will end up having, you have a 1. So I'm also going to take this 2 out. So we have a 2, and then you multiply by 1 minus e raised to minus a 2 there. And you still have a limit there as n approaches infinity. And then I took this in front of the integral. And then you will have, the limit. So I'll have 1 over n is what's going to be left, divided by 1 divided by e raised to 2 over n minus a 1. So that is basically what is happening there. So I still have a 2. I have a 1 minus e raised to minus a 2. And then inside here, I still have the limit as n approaches infinity. And then in the numerator, I will have 1 over n. And then here, I have e raised to 2 over n and then minus a 1. The next thing that we are going to do here, we're almost there. So we have a 2, and then we have a limit, and then we have an n approaches infinity. And then inside there, we'll have, in the numerator, we'll have n raised to minus 1. In the denominator, we'll have e raised to 2 times n raised to minus 1. Why am I doing that? Is because when we are taking derivative, it's easy to deal with that. And this minus 1 here is the exponent of n, to say that it was in the denominator of this fraction. It's minus. Next thing that we want to do here, I have a function in the numerator. I have a function in the denominator. Now, I want to end up making sure that I am taking this limit. If I were to plug in this infinity here, let's say I plug in this infinity here, I'll get 1 over infinity, which is going to be a 0. If I plug in here infinity, I will get 2 over infinity, which is going to be 0. E raised to 0 is going to be 1. 1 minus 1 is a 0. So we are having a 0 over 0. So we can use L'Hopital's rule when we are here. In other words, take the derivative of the numerator, take the derivative of the denominator, and take the limit. So we have 1 minus e raised to minus 2. And then here, we take the limit as n approaches infinity. What is the derivative of that? Is going to be, you bring the exponent down, you have a minus 1 times n minus 1, and then you subtract a 1 there. So we are having that. So this is just the same as minus a 2. And then you come here. What is the derivative of this? If this was e raised to n and we're taking the derivative with respect to n, it was just going to be e raised to whatever that is, which is just a 2 times n raised to minus 1. It was going to be that. But the issue now is actually not that. There is something in the exponent. So we have to take the derivative of the exponent. What is the derivative of that? We take the exponent down, so it's going to be minus a 2 times n raised to the derivative of that. Of course, we know that is going to be a minus 2. What is the derivative of 1? Is going to be a minus 0, of course. So we are having 2, 1 minus e raised to minus a 2, and then we have the limit as n approaches infinity of minus n squared divided by e raised to a 2 divided by n, because we have a minus, so it's in the denominator. And then times minus 2 times n minus a 2. And then, of course, we can leave that. I have minus here, this minus n squared, this one, and that one is gone. N raised to minus 2 and n minus 2. So these two cancel out. This negative and that negative, they cancel out. And we are left now with the 2, 1 minus e raised to minus a 2. And you have the limit as n approaches infinity of 1 over e raised to 2 over n, and then we have this 2 there times a 2. So that's what we are getting. We are almost there, because this is 2, we have 1 minus e raised to minus 2. What is the limit? of course this is going to be 1 divided by here. If you look into this, if I plug in infinity here, I will get 2 divided by infinity, and 2 is so small compared to infinity, so I will end up getting e raised to 0 times a 2. And of course this whole thing is going to be 2 times 1 minus e raised to minus 2 all over 2, because this is a 1, and this 2 and that 2 will cancel out, and you are having a 1 minus e raised to a minus 2. Therefore, the area enclosed, which is the same as, I have a 0 here and a 2 of e raised to minus x dx, it was actually simply as 1 minus e raised to minus a 2. That is what we actually got. I hope you are following the steps there. Now, let's look at number B. The particular antiderivative of, so let's first look at what we're doing at number B. Number B, we just wanted to find, this is the function. I want to see if what we did is correct. If it is correct, we're supposed to get the same answer. Of, let's say we have f of x, and f of x is equal to e raised to c of x. So if we are having that, the antiderivative of that is supposed to be f of, if you remember when we were doing the particular antiderivatives, we were having the antiderivative as 1 over c times e raised to cx. So that was the antiderivative when we're doing the particular antiderivative of that. But in this case, we are having our y is equal to e raised to minus an x. So when you are having that, the particular antiderivative of this now is going to be the same as in this format. But now you can see that here the constant is actually a negative 1. So we're supposed to end up having 1 over negative 1 according to that, because that constant is the number that is in front of x. So 1 over c, and then you have an e, and then when it comes to this c here, it was a minus 1 as it is, and then we have an x. So this is just 1 divided by minus 1 is minus e raised to minus x. So this is the antiderivative. Now, when you look at the f of 2 minus f of 0, this is going to be minus e raised to minus 2, and then minus, what is f of 0? Is going to be minus e raised to minus, in the place of x, I am plugging in a 0 there. And then, of course, when you look into this, this is still going to be minus e raised to minus 2. Minus and a minus is a positive, and then you have an e raised to a 0 there, because minus 1 times 0 is still a 0. So you end up having e with a minus, minus 2, and then plus a 1, or simply put, it is 1. I'm going to start with a 1 minus e raised to a minus 2. So this is f of 2 minus f of 0. What is that actually saying with all of this? You can see, I want us to actually highlight that and see, is it the same? It is actually the same as that. So our calculations are correct, and also our conclusion is actually correct. That is, you can see now that our area, which is the same from 0 to 2 of our given function e, f of x with the dx, is simply the capital letter f of 2 minus the small letter of 0. So that is what we actually ended up getting. So I want you to know that when they're asking you about the area, they are asking you about the same thing. They are also asking you about this, which is the same as that in this particular case. Now that we actually found ourselves towards the end, I want us to define what I call the definite integral. What is a definite integral? Let me write it here. The definite integral. What is a definite integral? I'm just gonna give you a definition here. Maybe you will be able to see it. I just told you that the area is the same as this thing, and also it is the same as that, and it is the same as that. That is actually the area, and you know how to find it. Let's start with a definition. A definition. So the first definition I want us to talk about is if f is a function. So we have f is a function defined. So we have f is a function defined for the interval a is less than or equal to x, less than or equal to b. This, remember, it is the same as a up to b. So this thing is the same as that. So we have a function that is defined there. So we divide, first we divide the interval. We divide the interval ab into n equal sub intervals. N equal sub intervals. N equal sub intervals with data x. So we have our data x, which is b minus a divided by n. We let x0 equal to a, right? And then we have x1, and then we have x2, and then we go all the way, we end up having xn, and this xn is actually the same as b, right? I will let this be the end points, of these sub intervals. So these are the end points of these sub intervals, and let x1 star, x2 star, x3 star up to xn star be any sample points. Be any sample points. So let this be any sample points in these sub intervals. So xi star is let me not say this, let me just say lies. Lies, so it lies in the interval xi minus 1 and xi, so it is in between these 2 points. Then the definite integral, the definite integral of f from a to b is given by. So let me talk about this. So basically what this whole thing is actually saying, I'm just gonna try and summarize it into a few points because it's what we have been doing, is saying that if, let's say, you have a Cartesian plane, these are x-axis, these are the y-axis, and you have a curve here, which is actually f, let's say f of x, and this point here we have a, this one is b. You divide this interval into sub interval. In other words, you create rectangles. And then after that, this point is the one, you call it x1, this one is x2, this one is x3, this one is x4, up until you have xn. And then secondly, you pick a simple point somewhere here. It can be this, it can be that. You can pick a simple point, and then you create, you project it to the function, and then there you create your height of each of the rectangles. And then this point is the one, you call it x star 1, and then you do the same thing here, x star 2, up until you arrive to the end. That's what this whole thing is actually saying, and it's actually telling you that these intervals are equal. That's what this thing is saying, which is what we did before. Then our definite integral, it is defined using this symbol here, a long elongated s, not s as s, and s as an alphabet. So you have this this a here, and then you have a b there. If you look at this a and b, these are the end points of the given interval. These are the end points of this given interval. And then here you have your f of x, and then you have your d of x. So this is actually what we call a definite integral from a and b, and it is defined as the sum. Let me not write it like this. It is defined as a limit as n approaches infinity of the sum from I is equal to 1 up to n of f of xi star times delta x. So that is actually the definite integral. Of course, you know that this is simply the same as n approaches infinity of the sum from I equal to 1 to n of f of just xi times delta x. Like I said before, this and that is the same, and also it is the same as n approaches infinity of the sum from I is equal to 1 up to n of f of xi times delta x. So this is actually by definition, this is the definition that is usually given by a textbook. This one here, these are the things, because when you're analyzing this, you'll end up finding out that this and that is one and the same thing. And for me, when I'm doing calculations using the definition, I usually follow this one. In other words, I set this xi dot, or the simple point, to be that point. I can do that because you need to choose a simple point. So this is the definition. What does that supposed to mean? It means that the area under the curve between these 2 points, or the enclosed area, is the same as the definite integral. This is actually the definition of a definite integral. And then if you look at this elongated s, it's an s, you can see you have a b, and then you have f of x, and then you have a dx. This one here, okay, let's start with this one, this elongated s. This elongated s was first introduced by Leibniz, and we usually call it the integral sign. So it is an integral sign, this s here, and then this value that is here, we call it the lower limit of integration. So it is a lower limit of integration, and if you look into this one here, we call it the upper limit. So it is an upper limit of integration. And then this f of x here, we call it the integrand. So it is an integrand. And then this one here does not have a meaning. Okay, this s here, the reason it is an s is because it is actually it is actually the sum. It is the sum. I want to repeat it. If you look at this one here, we have this symbol here, which actually saying we are summing the areas. So this s here is there to tell us it is a sum. That is why this symbol was s. That is the reason behind having this s here, not having a elongated m or l. This s was taken as the integral, the sum. It is a sum, and we call it the integral sign. And then this one is a lower limit, this one is the integrand, this is the upper limit. And then this one here does not have a meaning at all. It just tells us that the independent variable that we are focusing on in the given function is this x here. That is actually the meaning of it, and there is nothing more to it. And then the last thing that I want us to talk about here is this: the procedure of calculating. So the procedure of calculating an integral is called integration. It is called integration. So basically, just this whole thing here, we just say the integral. It is an integral, but this one's an integral sign. This one is the upper limit of the integration. This one's a lower limit. Integrand. This one is giving us the value. The process that we have to go through to actually find the value of this integral, it is an integration. So that is all there is to it. In other words, this one here is the same as the net area enclosed by the line x is equal to a, x is equal to b, the curve f of x, and the x-axis. So that is basically what is a definite integral is about. It is just the area. So all these things that we have been doing here in these examples, we were actually finding the definite integral. In other words, there is a lower limit, there is an upper limit. We have a function and it is enclosed or bounded by these particular functions. So that is where we are going to end at this particular point. We're going to end there so that at least you get time to actually get to learn more and practice as much as you can when it comes to this. So we are having that. Let's stop there.